Multithreading, or just threading for short, was one of the most baffling concepts when I first got into programming. I found it difficult to wrap my mind around how the code I write distributes to multiple CPUs, and how I should think about this from a programming perspective. Today I am recording this video because maybe you have the same questions I had back then. In the next 20 minutes or so, I'll cover basic terminology that you may encounter in discussions about multithreading, how operating systems use threads to implement multitasking, how to write code that utilizes multiple threads, and how your code executes on one or more CPUs. So regardless of whether you're just curious about what threading means technically, or maybe you've programmed with threads before but want to understand a bit better how it all works, this video is for you. If you're on a modern operating system like Windows, macOS, or Linux and use reasonably modern hardware, you can run dozens or even hundreds of applications in parallel. Here's a recording of my laptop running Fedora Linux from when I was working on this video. It ran OBS Studio, which is the software I used to record this video, a terminal window running HTOP, and a bunch of browser windows, one playing a music video, another one running a DOS game emulator, all at the same time. This feature of modern operating systems is called multitasking, and the OS achieves that by moving application threads on and off one or more available CPUs. If you grew up in the early 2000s or later, this may not impress you. However, before the mid to late 90s, this was basically unheard of, and most computers were only able to do one thing at a time. Take this game for example, Test Drive, which I enjoyed greatly at the time. You may have noticed it's the same game I was running in an emulator alongside dozens of other apps in the recording I just showed. When this game was originally released, the operating system of choice was MS-DOS. DOS only ever allowed you to run a single application. Computers were simply not powerful enough to handle more than one application at a time. You would enter the name of the executable file on the DOS prompt, and the application would pretty much take over your computer and nothing else was able to run. No looking up cheats on the internet while playing a game. Well, not that the internet existed anyway. The arrival of multitasking operating systems has been a literal game changer, and in programming we can take advantage of this using purpose-built multithreading APIs. Going back to the present then, this is probably a more familiar sight. The stereotypical smartphone app that needs to load some data in the background and displays a progress spinner at the same time. This is the app telling us it's doing more than one thing at a time, and it does that by running multiple threads of execution. One thread to perform the necessary background work, and another thread to render a progress spinner as part of its user interface. This allows the UI to remain smooth and responsive while doing the heavy lifting out of sight, so to speak. There are numerous examples of where threading is used today. Modern web servers, for example, use threads for performance reasons. Whenever a client like a web browser opens a connection to the server, that connection will be processed by a worker thread running concurrently with the main server thread. If it weren't doing that, then no other clients would be able to connect, while the server is busy servicing existing clients. This allows web servers to process thousands of requests every second. The gist is that multitasking is important and a basic necessity in computing today. So let's dive into the major ingredient that allows multitasking to happen. Before getting too much into the weeds of how threading actually works, I wanted to clarify some basic terminology. There are 4 terms that are all related, but don't quite mean the same thing. These are threading, concurrency, parallelism, and multitasking. It's hard to draw clear boundaries around these, but the way I like to think about them is using this pyramid analogy, where lower layers of the pyramid enable the layers above them. Multitasking then makes use of all of these techniques to deliver fast and responsive user experiences. At the bottom of the pyramid, we have threading. Think of threading as the technical building block or tool that enables concurrent execution of software programs. As a programmer, you can create new threads using software libraries in your programming language of choice. Creating a new thread this way instructs the operating system kernel to schedule it to run on one or more CPUs. It is vital to understand here that threading does not imply concurrency. It merely enables it. Any program you write for a modern operating system will always run at least one thread called the main thread of execution. If it remains the only one, we call the program single-threaded. If on the other hand, either you, the programmer, or the programming language runtime create additional threads, then we call the program multithreaded. Right above threading, we then have concurrency. Concurrency has a more abstract meaning and is more of a property rather than a tool in and of itself. It refers to the idea that more than one thread can progress at a time without running from start to finish in one go. In other words, concurrency allows programs to be interrupted and their instructions interleaved so that they either appear to run simultaneously, and I will show you in a minute what I mean by this, or actually run simultaneously. You can even write concurrent code for single-threaded programs using constructs such as coroutines, which are blocks of code that you can suspend and later resume, so concurrency is not the same thing as multithreading. This brings us to the top of the pyramid, parallelism. Given either a single program running several concurrent threads or multiple programs running one or more threads, if we also have access to more than one CPU, we can run them in parallel. Note that parallelism is not the same as concurrency. If we only have access to a single CPU, no matter how many threads we run, they will never actually run in parallel because they will all compete with each other to access that one CPU. Simply put, all parallel programs run concurrently, but not all concurrent programs run in parallel. Think about it for a moment. So what's multitasking then? Multitasking is more of an operating systems term and refers to their ability to manage multiple applications that all want their threads to run. The OS calls these threads tasks and uses a task scheduler to assign CPU time to them. Truly parallel execution on multi-core computers is also the secret sauce that enables modern multitasking operating systems to perform such feats as streaming music to my Bluetooth speakers while I am working on this video. Think about it for a moment. A world without multitasking would mean I'd have to listen to music for 5 seconds, then exit the music player, then open OBS Studio to record 5 more seconds of this video, then close OBS Studio and reopen the music player to listen to 5 more seconds of music, then you get the idea. Let's have a look then at how operating systems actually execute threads. In order to manage execution of multiple application threads, the task scheduler adds and removes tasks from a task queue so that each task eventually gets its turn to run. How much CPU time the scheduler assigns to each task and in which order they run depends on the scheduling algorithm and can vary between operating systems or OS versions. A simple scheduler might use a round-robin scheduling algorithm and let a task run, for example, for 100 milliseconds before interrupting its turn. The key takeaway is that the OS ensures fairness by regularly and frequently interrupting application threads and takes them off the CPU, so that other threads, either of the same or some other application, can run instead. This is called preemptive task scheduling because applications themselves can't really control when they run. They can only signal their intention to run. I'm mentioning this because you may come across the term, so now you know what it means. Take this example of some hypothetical desktop or smartphone OS. Here we have 3 programs competing for CPU time: a music app, a web browser, and the OS itself. Since the OS is also just a bunch of programs that need to run, the OS also needs to share CPU time with any end-user applications. I've talked about application threads a lot, but you may wonder how they differ from application processes. The explanation for this is quite simple. An application the OS has loaded from disk into main memory is called a process, and each process contains at least one thread. Think of a process as the runtime view of an application. When it exits, it's gone, and so are all its threads. So why not always create hundreds of threads when writing an app? Well, since it's not the entire process that is assigned CPU time, but its threads, they will not only compete with threads of other application processes, but also with each other. Plus, it takes work to move threads on and off CPUs. This is called a context switch and does not come free. So keep this in mind when programming with threads. While threads can make your app faster and more responsive, they are not a free lunch, and more threads does not always mean better or faster. It will depend on your exact use case how many threads are appropriate to run, but if in doubt, err on the side of fewer threads, not more. With the theory out of the way, let's get back to our sample app from earlier. How can we structure this app so that it performs work in the background, but also keeps the user interface responsive, for example by rendering this progress spinner? We'll first look at a naive solution that does not use threading and show which problems this causes. We will then improve our solution by introducing threads to make the app feel more responsive and smoother. Remember the color coding used here, as it will help you understand how different pieces of code fit together. I use green for code that performs background work and pink for code that updates the user interface, here the progress spinner. So finally, let's look at some code together. First of all, and this is true for basically any application with a user interface you will ever write, we should separate application logic from presentation logic. For this simplified example, our application logic deals with refreshing some data shown in green on the left. What this data is or where it comes from does not really matter. Loading data is often a slow operation because it typically requires accessing a storage volume or even the internet. So here we write a function called refresh data, which updates application data in 3 steps. First, we load it, for example by downloading it from the internet. Then we save it to a local storage so that it's easier and faster to access by the application. And finally, we drop any old data that has now become obsolete. While the refresh is ongoing, we want to update the user interface so that each time we call show progress, it advances the spinner rotation animation. This is shown on the right. It does not matter here how advanced spinner is implemented. Let's just assume it's able to update the spinner image by rotating it around its center by some degree each time it's called. So how can we combine these functions to run at the same time? If you're new to programming, or if you've never used threads before, then you may try to do something like this. In refresh data, we interleave the calls to loading, saving, and deleting data with calls to our UI update function. This would effectively advance our progress animation every time we made some progress refreshing application data. So are we done then? Well, this is not a great solution for several reasons. First of all, it would result in a janky animation. We're only performing 3 steps of work, so we only get 3 opportunities to advance the animation. Also, these steps may not take an equal amount of time. If loading new data takes 4 times as long as deleting old data, then the animation playback will be jumpy and anything but smooth. Also, we are now mixing application logic with presentation logic, which will get messy as our application grows in size and complexity, and UI update calls will be scattered around the application code. So let's practice good code hygiene and not do that. If calling update progress repeatedly from application logic is not an option, another thought you may have is to improve the code as follows. Instead of interleaving calls to data and view functions, we play the animation in a loop as long as we are still loading data with the help of a function called isDone. This helper function returns false as long as we're still refreshing data and true when we're done, so the loop can terminate. That way, we only need to call update progress once and let it run while we're refreshing data. This is definitely going in the right direction, but now we've created a new problem. The problem is that, as mentioned earlier, programs run in a single thread of execution when they first start. Since in imperative programming, instructions execute in the order you list them, the call to update progress is what's called a blocking call. When the program enters this function, it will also enter the while loop that animates the spinner, but this loop can never terminate because isDone will never return true. Why will it never return true? Because as long as we are literally spinning our wheels in the animation loop, the program cannot call any other code, so it never gets a chance to run through the remaining calls that load our data and signal the UI that it's done. This unreachable code is shown as crossed out here. So what do we do when we are dealing with blocking calls that prevent us from making progress? Well, we create a fork in the road, so to speak, by placing that call on a new thread. Here is how we can solve this problem by running UI updates on a separate thread. As mentioned earlier, applications always start execution on the main thread, and this is where we enter our refresh logic. Unlike before though, we rewrote update progress to run on a new dedicated thread. Keep in mind that I'm using pseudocode here, and how exactly you do this differs from language to language. The 2 key things to take away here are that first, any code scoped to the thread keyword will execute concurrently to the main thread, and second, executing a block of code this way means its execution is somewhat delayed and the update progress function will return immediately after the new thread is created. This is what turns update progress from a blocking to a non-blocking call. Technically, what happens is that we are instructing the operating system to perform a context switch, so that both the main thread and the UI thread are allocated a slice of CPU time to progress through the instructions regularly. Back on the main thread, once it resumes, we can now immediately proceed to the code that performs the actual loading of data, which has now become reachable. You may ask, when creating a new thread this way, what happens just after you do that? Will the UI logic run first, or will we continue to run on the main thread for a while longer? The answer is that this depends on the operating system's task scheduler, and you cannot really know. That's why you should never make any assumptions about the order in which instructions actually execute when they run on different threads. In fact, this uncertainty is what creates an entire class of problems arising in concurrent programming, such as data races, dirty reads, deadlocks, and so forth. But we will not get into these today, as that is an entire topic by itself. Now let's look at what happens to the task queue we introduced earlier, which should help visualize these mechanics better. First, our main thread executes, which calls update progress, then our UI thread gets a chance to run and does its thing, and finally some other thread, here an operating system thread, also gets its chance to run. Each of these threads will get around 100 milliseconds of runtime, but this is just a rough estimate. Also, it's vital to understand this is just an example of one possible scheduling scenarios. It could also happen that the task scheduler decides to let the OS thread run first, and then your application's UI thread. It depends on things like the OS you use, the scheduler implementation, hints your program can give to these schedulers like thread priorities, and task statistics such as how often a thread has run compared to others in the past. For example, Linux uses a scheduler called the completely fair scheduler that prioritizes tasks that haven't run in some time so that no single application can claim the lion's share of CPU time and thereby starve other threads. I mentioned before that interrupting a thread's execution by the scheduler so a different thread may run is called a context switch. I thought it might be interesting to see how that works in practice because it will solidify your understanding of how program code, the OS, and the hardware interact. Here we have a CPU and the two application threads that are competing for CPU time. Currently, neither of them is running. Note that I'm not including any other threads that may want to run, just to keep things simple. On the left is the main thread and the instructions for refresh data, and on the right is the UI thread and the instructions for update progress. If the code looks like gibberish, that's because it kind of is. Truth is, the program code you write in a high-level programming language cannot run directly on the CPU. It is first compiled into instruction sequences the CPU can understand. The simplified instruction sequences I show here are only used for illustration purposes and are completely imaginary, but should give you an idea of what the CPU actually sees. For example, the while loop in update progress was compiled into a comparison operation that is used to test the loop condition, the actual loop body, which I omitted here, and a jump instruction that moves program execution back to the beginning of the loop at instruction 1. That's right, there are no loops once your code reaches the CPU. Instead, it jumps from one point of the program to another. Branching logic using if-else constructs is translated in a similar fashion. But enough about that for now. Let's see how context switching works in practice. Our main thread runs first and wants to call fn2, which represents the update progress function. When running code on the CPU, function names don't exist anymore because this information is only useful for humans. All the CPU sees is a memory address, which might be stored in a CPU register, and this is what I called fn2 here. The CPU also maintains a program counter, which is sometimes also called the instruction pointer. The program counter, or PC for short, holds the memory address of the current instruction sequence. This way, the CPU always knows what to do next, as the PC moves over the program's instructions. Now in update progress, or here fn2, we start a new thread. So when we enter this function, a context switch occurs and the UI thread can run its own instructions instead. To perform the context switch, the task scheduler takes the main thread off the CPU and stores its program counter value. When the main thread gets its turn again, it can then restore the PC and resume the program exactly where it left off earlier. When the context switch is complete, instructions from the UI thread are now on CPU, and the current value of the PC now points to the start of the loop. The UI thread then progresses from there for the assumed 100 milliseconds or so. When that time slice expires, another context switch occurs and it's the main thread's turn to run. Because we stored the program counter earlier, we can resume exactly where we left off and progress for another 100 milliseconds. In this case, it's executing instructions for calling into the various functions for loading our application data. This back and forth continues until all instructions have run their course. Remember that we will terminate the loop in update progress once the main thread has finished loading data. This results in the comparison instruction in line 0 to evaluate to false, and another jump to the final instruction occurs. Once that happens, we return from the function indicated by the ret instruction here, which is short for return. Because that's all the UI thread had to do, the thread exits and we only have a single task left, our main thread. The main thread also eventually progresses to return from the refresh data function we started out with. And that's it, we're done and the CPU has become idle, at least as far as our example goes. In practice, this will almost never happen. First of all, our application would probably want to run more code to be useful and not just exit. And then there are likely other applications that require CPU time, not least the OS itself. I still owe you one more answer though. We never really talked about the differences between concurrency and parallelism that I mentioned at the beginning of this video. Since we've covered so much ground already, this is now much easier to explain. Just take everything we've been doing earlier, add at least one more CPU, and you get parallel code execution. For example, with 2 CPUs, we can do twice the amount of work, and our threads can actually execute their instructions in parallel instead of taking turns on a single CPU core. Of course, even with 2, 4, or really any number of CPUs, we are still limited by the number of threads we can run simultaneously, so we still need all of the machinery I walked through earlier so that all threads eventually get their turn to run somewhere. I hope you see now why I waited to talk about parallelism. It is much easier to understand when you already have a good grasp of what concurrency means and how program code can be structured into multiple threads of execution that are scheduled individually by the operating system. We've covered a lot of ground in this video, and multithreading is a complex and difficult topic, which is why I'm making this video. But I hope that by addressing the subject holistically rather than focusing on just one aspect, I improved your understanding of threading fundamentals. Let's summarize briefly what we covered. If there are 3 things I hope you took away from this video, it would be: first, modern operating systems can handle large numbers of threads, which they call tasks, and which the OS schedules to run on one or more CPUs. Second, you should now know that threading is the mechanism that allows for separating the programs you write into logical slices whose instructions are interleaved and that run concurrently even on a single CPU. Finally, a major takeaway should be that parallelism is just threading plus at least 2 CPUs that we can schedule threads on, so that their instructions can physically run at the same time. That's all I had for today. Thank you for watching. Please like this video and subscribe to my channel, as this will help others find these videos and will encourage me to make more.